Friends, today we are going to present about the senior project. Our project is application of Autoencoder in multiple input, multiple output in wireless channel. Project code is WRSG1 and our advisor is Professor Vinusak Santipat. Let's talk about that we will talking today is mainly three parts in our topic. First is overview and objective, and second is relay theory implementation process and results discussion, and the last part is conclusion and reference. And let's go to the overview. This project is aimed to improve the efficiency of multi-input and multiple output wireless channel in communication system by integrating deep learning capability, especially for leveraging autoencoder to the conventional MIMO system serve as baseline for comparison with the autoencoder enhanced system designed to surpass its performance. And the objective is to utilize the autoencoder in MIMO wireless channel to enhance the performance of overall MIMO wireless communication system. Firstly, let's talk about the mainly of relay theory of in this project. Let's go to the deep learn in the physical layer. The key idea of this theory is to represent transmission channel and receiver as one deep neural network that can be trained as autoencoder, that you can see in the figure under the description. Firstly, we will get the transmitter channel receiver into one block. That the traditional is need to make in digital communication in the single block, but this make the digital communication compressed into one block. That is told. And the potential of the deep learning is to offer the advantage of not needing a perfect mathematical model and can adapt to specific hardware and channel condition potential, improving performance in presence of these imperfects. And this can remarkable ability to approximate the mathematical function present advanced have shown that quality learned algorithm even those complex during complete computation. And here is the example of the deep learning basics. Here is the feed-forward neural network that is the convolutional neural network. At firstly, the picture is split into the input in the input layer of the deep learning neural network, and each circle, each neuron is spread the mathematical function to activation function and anything to go to the output, hidden layer to the output, and go to classificate that this is a bird or whatever. And here is the example of the convolutional neural network. Firstly, the input is go to the hidden layer, and is the metric that call the is the metric that the dot product between two metrics. The firstly is the set for the learnable parameter, otherwise known as the kernel, and the other matrix is the heuristic portion reception, that is the input that the matrix is used for that's the picture that input the is for this data matrix, and it's dot together like the right figure that's showing, and it will show the activation, it will calculate the activation map and calculate to have the one hidden layer, one neuron in each layer. And this is the mainly part of our project is the autoencoder. This is a unsupervised feed-forward neural networks. That's no label needs. The purpose of this autoencoder is compress input data into the lower dimension and reconstruct them into original data from the compressed form that input in. And autoencoder are composed of two key of fully connect feed-forward neural network. Firstly is encoder. This encoder is compress input data, removing noise and capturing essential feature to generate latent space or bottlenecks in the middle of figure is L3. The decoder is reconstruct original data from the compressed representation obtained from the encoder. And here is the things that we do, the autoencoder for end-to-end communication system. This is the architecture that we will do in this project.
Okay, first, next we're talking about our implementations. As my friend have mentioned before, that our goal is to integrating the machine learning technique, which is the new technology, with the communication model that existing before, to enhancing the performance and minimize the complexities of the communication systems. So, next slide, please. So in our implementation timeline, we divided into three parts. First is we trying to conduct the traditional single input, single output communication simulations in Python in Google Colab to let this one be a benchmarking with the one with autoencoder involved. And the next steps is we try to implementing the model which is use autoencoder to involve. But first we to how can I say, to familiarize ourselves with the machine learning technique, we try to implement it on just single input and single output communication simulations. And finally, we have found, and we try to use the model which can compute the bit error rate in multi-input, multi-output or MIMO communication simulations. So this is basically three steps. First, I will talking about the conventional communication model that we have designed. In this case, is we designing the single input, single output. And as you can see, so as you can see in these slides, there's lots of components, including the input informations and the channel encoder, modulator, wireless channel demodulator, decoders, and output information to calculating or to visualizing the output or performance of this model. We are using two things, which is input information and output information, and yeah, basically that. Next slide, please. First, our function in single input, single output model that we have simulated is the encoding part, which is, of course, they'll need to be coming up with the decoding function. So this basically the two functions that we have implemented. First, in the top one is the encode functions. In this project, we decided to use the Hamming encoding, and the code that I have provided in the screens, it's the Python coding, which is which can implementing the Hamming code 7-fold code rate. But actually, this encoding technique have just one limitation, because it can just detect an error and correct it just one bit. If there are more than one bit of error, they cannot be finalized and correcting it. So basically, we use Hamming 7.4. Next slide, please. And this is in this slide, I provided you the modulations, code functions, and of course come up with the demodulation function. In this case, we decided to use the QPSK modulation technique because in next steps, there's the channel, and the channel we using as discussed with professor that we are going to use the Rayleigh fading because it's simple and yeah, and we have the additive white Gaussian noise, which all of that have the real components and imaginary components. So QPSK might be the good choice to come up with, and this is this I have provided you the function of the modulation in QPSK. Next slide. So next, let's talk about the essential part, which is the channel and Gaussian noise. As I mentioned before, that in this project, our channel will be Rayleigh fading channels and the additive white Gaussian noise. And I will show you that what Rayleigh fading and additive white Gaussian noise can do. But actually, let me how can I say? Let me explain to you what is Rayleigh fading. As shown in the figure in the right side of the screen, there's lots of a path that the communication might propagate in our real life scenarios, including the lines of sight and the another scattering paths. In Rayleigh fadings, we do not consider the line of sight part, which is the line of sight part is the strong they have a strong power and have yeah, but in Rayleigh fading we just consider the scattering parts with no line of sight. And talking about the Rayleigh fadings, of course, when we transmit the symbol or the data, we denote it as X, and the channel, whether it would be the Rayleigh fading or the Lysian fading, we will denote it as H, and the noise we denote it as N. At the receiver, we can receive the channel by H multiplied by X and plus N, which is that I have mentioned before. Next slide. And this is basically the code function that we have implemented is in this code functions. It is including the fading coefficients, and moreover, it's including the noise, additive white Gaussian noise, and the match filter at the receiver. And this model can implement correctly. Actually, next. In this slide, we will talking about the calculation of bit error rate, which is bit error rate equal to the number of bits in error over the total number of the transmitted bits. And actually, next slide, there will be the code function that I have write it. And this is a result. The right one is the one that I have write the code and implemented, and the left one is the benchmarking that we have found in the internet. You can see in the left side and the right side. The right side have slightly actually better result because we have including the encoding techniques which can implementing the error collections. So it's will making the bit error rate slightly better than the left one with no encoding techniques. Next slide. So after we have done that simulations in conventional communication model, we're trying to integrating the autoencoder techniques in the next semesters, and I will mention next. In this autoencoder technique, we have lots of trouble about conducting the Ley fading channels. And after we have scattering around the internet, we found this model, which is with the channel have generating in MATLAB, and we just plug in the channel in the model, in the autoencoder model. As it's have mentioned in screen, the right side is the coding of the MATLAB functions. In this coding is both is just including the H, which is the channel, and this is rarely fading channels. Next slide. And first steps that we need to do is we need to define the parameters is shown in the screen. The M is the number of message, and the K is modulation order. The N is the channel dimensions, and R is channel rate. And we need to define the signal to noise ratio that we will use to train the model. And next is the autoencoder architecture. At first, we need to develop the neural network models, which have mentioned in the screen, including the encoding part and the decoding parts. And moreover, in the channel, in the middle, that states as the channel layer, we input the channel that we have generated from MATLAB and plug it in this model in the channel layer. So basically, this model will have two inputs, and which is two input, which is the data and the channel that we have generated from MATLAB. And when it comes to machine learning, of course, it needs to be training the models to make it able to optimize to enable it to work properly and work it most accurate as it's possible. And as a previous slide, two previous slide that I have shown you the neural network architecture. But in autoencoder, we need to extract out the encoder part and the decoder part and tell them which one is encoder and which one is decoders. And this is a code that we have write it, and we have defined which one it will be, which layer will be encoder, which layer will be decoder in these slides. And this is the taste data that we will generations to compare it and calculating the bit error rate at the end to checking the performance whether it's working better or worse than the conventional model that we have developed. And this is the bit error rate calculation function in the screen, but yeah, this is the bit error calculation functions. And next, this will be the result of the model that we have developed. The left side is the model with the autoencoder involved, but the right side is the traditional model or conventional model that we have implemented in the first semester. When we look closer in signal to noise ratio at 20, the left side tends to perform better than the right one because we're using the autoencoder to help us to maximize the performance of these communication models. And we're guessing that we are coming in the right way. And next, we were talking about the MIMO communication simulation. So, Pim.
Okay. I will talk about MIMO communication simulation of the autoencoder. Firstly, this model is implemented by J.S. Charmer. It's pop up in the GitHub, and this model is implemented by PyTorch with neural network operation. It's perform the import matplotlib sci-fi loading data and the progress bar keras utilized as like one hot autoencoder. Firstly, this model is defined system by the parameter. M is the number of modulation, and n underscore t is the encoder hidden layer, and n underscore r is hidden layer of the decoder. Firstly, let's classification of the encoder. Let's make the architecture of the the encoder part. Firstly, we use the fully connect with 3 hidden layer with Liru activation, and the last the FC3 is output side is a corresponding to the transmit signal. And let's go to the decoder. For the decoder is compiled with 4 fully connect layers with Liru activation function again. And for the output, which log for softmax, the output side is concentrate for receive signal channel state information. Output is M represent to the decode message. And here is the section that we're trying to find the firstly come of this file that the implementer do. We pass the weight into each checkpoint for the channel of 4QAM model. For simulation loop, firstly they generate the random message and corresponding for the encoder label, and he's generate the random channel state information in very fading, then encode with the message obtained transmit signal and simulate the transmission by adding noise with signal based on current SNR, and decode the received signal using the decode along with channel state information. Then calculate the symbol error rate comparing decode message with original message, and update the error and symbol count. Lastly, that he do is store the calculation symbol error rate value for each SNR value. And here is the result of this implementation. We implement the Raytheon that you can see in the purple line is the QQSK Raytheon that we implement in this model, and 16 QAM Bayesian fading in this model. This model is can run for the 16 QAM is there's a problem in the 16 QAM because the SNR can run only to 16 only 16 SNR that we found it. But the model is okay for watch the efficient performance of the Rayleigh and Raytheons. It's true. By conclusion, firstly, the state of Python-based visualized Hamming code encoding and quadrature phase shift keying modulation within Rayleigh channel environment. This simulation offers insight. The essential factor includes improve the MIMO communication system, and when we implement the model that incorporate autoencoder, it presents several advantages compared to traditional model such as complexity and improved bit error rate. Autoencoder model performance show that the transmission efficiency improved with increased modulation order, And we have begun simulation using a Bayesian channel and extend beyond the scope of the project. In this simulation, we set the Bayesian factor is equal to 10 and defining indicate the performance in region fading markable exceed that very fading is work or not. And here is our reference. Our reference is come from the IEEE. First project is Introduction to Deep Learning for Communications and Networking, and second is Deep Learning for Wireless Communication and Emerging Interdisciplinary Paradigms, and third is Machine Learning Approach for Figurable Intelligence Surface. And lastly, we use the benchmarking end-to-end learnable form of the MIMO physical layer communications. Thanks.